Previously, we discussed how an electric field pushes randomly moving electrons that leads to a net drift velocity. We call this net electron flux a drift current. A net electron flux can also be produced from a concentration gradient of the same randomly moving electrons. Electrons will diffuse from high concentration to low concentration. We call this the diffusion current. To understand drift and diffusion, especially in junctions, we will be considering how the band energies and Fermi level may change with position using block diagrams where the bottom axis is position. In the simple case where there is no external voltage applied to either end and the doping is uniform throughout the semiconductor, the free electrons fill the lowest energy states so that at equilibrium the Fermi level is a constant. Not only is there no external applied voltage, which we call zero bias voltage, but there is charge balance at all locations, so there are no internal voltages produced. If connected to a voltmeter, it would read 0 volts because there is no electromotive force between the two ends. This is indicated by the Fermi level being the same at both ends, where, recall, the Fermi level is the electrochemical potential of electrons. This would also be the case for differently doped, but still uniformly doped, materials, such as more heavily doped N-type or a P-type material. Here, the Fermi levels are different relative to the band edges, but Fermi levels within the material are uniform, and still no voltage difference would be measured across the materials. When a voltage bias is applied across a conductor, it raises the potential energy of electron states at one end relative to the other so that electrons will flow. Electrons in the conduction band can reduce their energy by moving here to the left, even without having to jump to a different state. Holes can also reduce their energy by moving upwards to the right. If holes and electrons are supplied by contacts at both ends, a steady state of flowing electrons and holes is produced. When the electrons and holes reduce their energy, this energy is transferred to the atom vibrations as Joule heat. In this non-equilibrium but steady state condition, the Fermi level follows the bias potential energy because it is the electrochemical potential of electrons, which includes the electric potential energy. A voltmeter measuring between the ends of the material will read this change in Fermi level as the electromotive force supplied by the bias voltage. The vacuum level, the energy where the electrons are no longer bound to the material, has the same potential drop as the electron states and Fermi level. Thus, the work function to remove an electron at the Fermi level to the vacuum has not changed. Only the electrostatic potential of the electron once outside the material differs by the bias potential energy. Notice that the diagram looks bent because of the electric field in the material. We sometimes call this band bending. Imagine now that we make a non-uniform conductor, for example by doping silicon N-type more at one end than the other, the left end having more electrons and a higher Fermi level than the right end. Such a Fermi level difference would induce electrons to flow from the left to the right. This difference is also associated with an electron concentration difference, so that we can call this flow of electrons down a concentration gradient a diffusion flux. The diffusion makes the right side negative and the left side positive, which would induce the opposite flow of electrons, or a drift current. The electrostatic separation raises the energy of the electron states on the right and lowers the ones on the left. This continues until the electromotive forces on the electrons balance, meaning the Fermi level is a constant. This can be drawn as a bent band diagram, where the electric potential energy bends the bands. Notice a constant Fermi level makes it higher in the lower end relative to the conduction band minimum, consistent with there being more electrons at that end, while the other end has fewer electrons and a Fermi level closer to the conduction band edge. In equilibrium, the Fermi level should be constant throughout the material. This is because the Fermi level represents the total electrochemical potential, the sum of the electric potential, which increases, and the chemical potential, represented by Fermi level minus the conduction band edge, which exactly decreases to compensate. Because the Fermi level is the same, there would be no external voltage measured by a voltmeter across this material. The electric field produced is said to be entirely internal. We often talk about a drift current and a diffusion current, which can be added to give the total current. The drift current is the current produced by an electric potential according to Ohm's law, and the diffusion current is produced by a concentration gradient, which is related to the chemical potential according to Fick's law. The signs are determined by the sign of the charge carrier. Because the same charge carrier is involved with both processes, the diffusion coefficient is related to the charge carrier mobility by the Einstein relation. The Einstein relation can be derived by considering the particle that diffuses has the same mean free path as the particle with a drift mobility. Here we will use a general derivation that relies on the relationship between the charge carrier concentration N and the energy of the charge carrier. For a semiconductor where Boltzmann statistics is a good approximation, N is related to the exponential of the energy difference between the Fermi level and the band edge divided by kT. In equilibrium, we saw this energy difference is related to the electric potential energy EV. Equilibrium also requires the drift current to exactly cancel the diffusion current. This requires the mobility to be related to the diffusion coefficient times the relative change in N per change in V, which becomes d log n dV. This is simply E over kT, giving the Einstein relation. The relationships for electrons and holes are similar, where we generally have different mobilities and therefore different diffusivities for electrons and holes.